Wait, there's one. Oh, I see. Okay. Okay. Thank you very much, and I give the floor to John.
Thank you, Solomon. So, also very welcome from my side. So, my name is Andreas. As you can see, I also work for the IU. I just wanted to say a couple of things to start to basically set the scene for you. So, the IU does, in one of its work streams, learning and working papers. So, it does not only work on evaluations, it also tries to look at the forefront of research and try to understand what are next steps in the right direction for the unit as well as for the fund. In that sense, we have put together a working paper to better understand what complexity is from the perspective of evaluation. That working paper is already printed and you can find a couple of copies up there. If you're interested, it's also online. It's also available online. But of course, our perspective doesn't take justice to the entire field of complexity science and complexity research. So we reached out to different universities and we found a very good collaborator here, which you will hear in a bit, to present on complexity from the perspective of a complexity scientist. And in order to set the scene, I just wanted to give you 3 slides. So one is, you all know, we all think about climate change and climate finance here at the GCF. So you all know, based on the landmark of the Paris Agreement, we know that the developed countries have committed to devote $100 billion every year by 2020. And we all know, as we all work for the GCF, that the GCF, as one of the institutions, has already started with this, funneling funds to projects in adaptation as well as. So far, so good. What we found is that most of those projects have a strong commonality or a strong link to development projects and development programs that are out there in the world. And so that's very interesting to see that's happening. But there's one distinct difference. If you look beyond all the similarities, you find that climate change as such is a very fundamentally unique and complex challenge when you think about projects. In what way? Well, we thought in a way as we look at problems and their solutions, we find that they are here when we think about climate change, they are large scale, they're interdisciplinary, and they are mostly uncertain. Oh, and in addition to this, we also find when we look at how we go about to understand these complex projects, we find there's very weak or no evidence base to be sure that this intervention that we plan will fully translate into an outcome. So in that sense, we're not fully clear of what works and what doesn't to reduce greenhouse gases and strengthen reserves. So in that sense, this poses a question when we think about evaluation. So when we look at the design of projects, we find that here, thinking about climate change programs and projects, we have a multitude of interventions. That's also a distinct difference from most of the development projects. And we also try to achieve, as designers of climate finance project, a transformational change. And when we look at the question of a multitude of interventions, we have to respond to the possibility of interacting interventions in different sectors and different fields, maybe even in different countries. And in that sense, we may face that problem of emergent outcomes. So outcomes that were not planned, given the theory of change. And in addition to the question of emergence, we also have that existence of unknown unknowns. So when we work in this space of climate finance and climate change, there's a high level of uncertainty that we face. And through that, it's very difficult to predict the behavior of the environmental side of things, the environmental space, as well as the human space. Because we're thinking here about the question of the last mile, the question of how does that really translate into different behaviors, and how can we predict those behaviors. In addition to this, we also look at the question of, and how do we understand innovation? So how do we link innovation into this, and how do we predict innovation in the climate finance space? So I give you two graphs here, two figures. So figure A basically shows you a traditional theory of change model, the traditional logistic model that we have. We look at the input, we look at the output, and then we look all the way up to outcome and effect. Right? But as I just said, since we are looking at a multitude of interactions, and those interactions have as well as a certain uncertainty with them. So there's a certain non-linearity to all of these effects. It's very likely that we sometimes missing the point when thinking about what is that particular effect, and can that particular effect be causally linked to whatever we have done in terms of intervention. So I've given you a figure B to simply show you what in the science of social networks is being done currently. So they're looking at all the different nodes that represent agents and all their interactions in between. So just to give you that visual idea of how that could be done. And in that sense, that presents also that difficulty for us as evaluators, because we need to think about what are our standard approaches and how can we translate those standard approaches to look at the new arriving problems that we face with climate change. And that's a very interesting field where we felt, okay, from our perspective, we needed to get further insights into what are complex scientists thinking, or complexity scientists thinking about this, and how are they explaining complexity? How do they look at the different features of it? So in that sense, I just want to end with that point saying, okay, we need to look at new methods that look more at the system-based approach rather than an intervention-based approach. So that's basically that point of this slide. So what have we done? So we went and we coupled up with the University of Bristol Mathematics Department, here represented by Dr. Karoline Wiesner, and we looked at four main questions. We looked at the questions, okay, what do we know about complexity theory? It's a very new field. What can we say about this? How does that link? How do people from the complexity science field understand behavioral changes? How do they look at governance? How do they look at climate risk? And then we also wanted to know the question, of course, we're not looking at like development programs would usually tend to look at one sector. We look at a very variety of different sectors in the same. So we look at more of a, what we would call a programmatic approach. So we wanted to see, okay, and how can we link this across different sectors? And what do we know about that in terms of complexity? And then the last 2 points were, okay, and what do we learn in terms of project design? What do we see there? How can we approach this when we have non-linear behavior? And from the evaluations perspective as well, how can we look at the complex structures and better understand them in order to evaluate them? Okay, without further delay, I now hand over to Karoline to give you a little bit of an interesting insight into our work and how far we've come so far. Thank you.
Very much, Andreas. Slides. Thank you. Good. Well, we've seen the title, so let me dive right into. I'll spend the first few minutes on telling you what complexity is, because we all know the term, but we probably have very different understandings of it. So from the perspective of a complexity scientist, here's a brief 3-minute introduction into, this didn't work. Courtney, do you know how to do this?
Okay, I think it's working now.
No, it's not. It's, or if you go here, maybe try this one. No, it's not
It's
working.
not working either.
Okay, well, I'll have to live with it.
Okay.
Okay, Okay, well, we get some technical help here. Let me start. You can already see this. So I've given you one example of a complex system. This is a visualization of the airline network across the globe. So, you can see all the main connections that we know about and colored roughly by local area. This is a complex system, and I'll explain to you in a moment why. In fact, we have two complex systems here. We have the network itself, which is the network of airline connections. So anything, any route you can travel on a commercial flight. The network itself is changing over time. New routes are being introduced, old routes are being taken out. On top of that, we have another complex system, which is actually the people traveling on that network. So the flow of people and goods that flows along that network is also a complex system. It changes constantly. It's a dynamic system. And so both of these are complex systems. And they are interacting, of course, because if the network changes, the flow will change. Flow changes, the network. Fantastic. This looks very promising. Thank you. Great. So here we have the first few set of features that we find in all complex systems. So we have many components, many interactions. That should be very clear why the network that I've just shown you is such a complex system. They are dynamic, they're never static, they're never standing still, and they are always open to some kind of environment. What's the environment in the case of the network? It would be, economic environment, it might be ecological environment. If a volcano breaks out, it will change traffic flow. Things that are not under the control of the system, but that have an influence on the system. These are not specific to complex systems, but they are actually very important to think about. And they lead us on to the particular properties of complex systems. So amongst them are self-organization, that's a term I referred to, the patterns that arise out of the many interactions. And nestedness is a nice one in the case of the network, because we have the global network that spans major airports in the world. Then we have more regional airline networks that are, if you like, underneath it. So if you want to get to a smaller city, you first travel via the large scale network, then you move on to the small scale. Okay. Adaptive behavior is another property that I show you here with the second example. That's the complex system of an epidemic or pandemic. So what's the complex system here? We have a virus, and that's spreading from host to host. And what we see is, this is an example of work of colleagues who looked at the spread of SARS, and this shows you the districts of Hong Kong. And what happens is, can I do this? Oh, fantastic. Okay. So this is colored by area, the number of outbreaks of that virus over time. So we can see it spreading slowly within the city. And then here is a mathematical model. So that's what complexity scientists do. They take data, and they take an understanding of the system, and then they put in a mathematical model. These arrows are effectively differential equations, and they quantify the probability of a person that is initially just there, susceptible. What's the probability of that person being infected? It depends on the surroundings, depends on how many people they meet every day. What's the probability of that infection actually becoming lethal? And then either they will die or they will recover, and they might be immune then, or they might be susceptible. So underneath this is a mathematical model. You put that together, and you ask yourself how many people are there, and then you can make predictions. So that's the whole idea of taking data together with a mathematical model. You make predictions about the spread of the epidemic, and you can then play around with this. You can come up with scenarios. For example, if we just let things go, what's the probability of people being infected? Everything will happen very quickly and very drastically. If, on the other hand, we have a scenario where, say, we are able to hospitalize 80% of the people who are infected, then that will give us a different prediction of the number of infected people over time. And that's the use of these mathematical models, that they use the data and they play around with the data to give you scenarios for possible happenings. Here, they've put these two things together. So they've put together the epidemic complex system with a network. And then, it became clear very quickly that this is spreading via the airline network. And initially, they were looking at, well, where is the virus going to and how quickly? Right? So it's starting in China. Well, it comes to Korea shortly, actually quite a lot later, although Korea is very close to China. So, while it comes to the US, very quickly, although in a geometric distance, the US is very far away. But then you put these two ideas of complex systems together, which is the endemic spreading itself, plus the airline network, and suddenly you see a pattern emerging, which is actually what notice here is a different type of distance. And once you've understood that, you can predict where the virus is going to go next. And you might know that the World Health Organization managed to contain this pandemic very quickly within a few months. And this sort of thinking did inform that, because they did target airline traffic immediately. Good. So that hopefully gives you an idea of the kind of concepts that are relevant in complexity. And also what is important is that it is always about mathematics, mathematical tools, and data analysis. So nonlinear dynamics, statistical mechanics, all sorts of different tools are being used to think about the phenomena that we observe: self-organization, nonlinearity, feedback, and so on. Okay, that was a whizzing tour through what complexity is. Clearly that leaves a lot of questions. But where we are now is, so here I'll give you a summary. That's a lot of the work I've been doing over the last years. You find that all on my website. A complex system is many components with many interactions between them, open to the environment in some way. The feedback from previous interactions gives rise to emergent properties such as self-organization, nonlinearity, adaptive behavior, and others. Pattern formation, outbreaks of disease. Now, how do we go from that scientific discipline to what the GCF is? So here, we are with all these mathematical tools and concepts, and there the GCF is on the ground trying to solve very urgent issues. I want to give you a quote by Elinor Ostrom, who won the Nobel Prize in 2009 in economics. She says we should stop striving for simple answers to solve complex problems. So I couldn't agree more with her. And in fact, I took her work where she came up with a framework in which to think about social ecological systems. And not just in a static way, but in a dynamic way, in the sense that we think about all the interactions that there are. So her framework informed very much the work that she was doing, her group was doing, and others on governing the commons, so resources that are being shared by groups of people. The basic idea is that all these systems contain, well, the resources themselves. So, for example, a fish population, the resource system, that might be the Atlantic, a particular coastal region. There's a governance system. There's always somebody responsible, setting up the rules. And of course, there are the users, fishes, for example, local population, global population. And these are all interacting. The system is never closed. It's always subject to political context, social context, ecological context, of course. So this is precisely the kind of viewpoint that a complexity scientist would take. What are the relevant parts of the system itself? How do they interact? And what else is out there that influences the system? So I decided to take her framework and tweak it slightly, extend it slightly, so I'm leaving out lots and lots of details here. But effectively, I'm taking her idea of having core systems, governance, environment, so on, and each of these core systems, so these are the core systems: the environment, resource system, user system, governance system. and then subsystems. This is just an example. Okay. So in these core systems, you might have the environment, that might be the climate, could be other things as well, could be economic situation. Resource system, an ecosystem, this is very general. User system, that could be different things. It could be enterprises, local population, local government. And then we have variables inside of these subsystems. So we have a nested view of our system. These variables are then, again, these are just examples, things that we can measure, quantify in some way. Might not be easy to quantify them, but it is in principle possible. So the relevant variable in the climate could be, for example, the frequency, if that's relevant for the particular project that the GCF is looking at. Or user system, that could be tourism enterprises. Now, so this is, I call this framework SEEDS, social, ecological, economic, dynamical systems. So we're adding a dynamical component here, but the bedrock is Ostrom's framework. And once we have this, what we are interested in, of course, is how do these things interact. So, we are taking all these variables, things that we can measure about a given system that the GCF might intervene into. I'll say more about that in a moment. And then we are looking for correlations. So these correlations can be found by, well, reading the project proposal. That can be found by asking people on the ground. Lots of different ways in which you find these correlations. For example, the frequency of the drought will affect the health of the land ecosystem services. Or employment of the local population will, of course, affect the subsistence of the local population. So you identify these causal relationships, and then you ask about these causal relationships: are they negative, are they positive, for example? So if the employment goes up, the subsistence goes up. If the tourism goes up, you might argue that the health of the land ecosystem goes up. So you identify properties of these. They could be positive, negative, be weak or strong. They could happen on a fast time scale or a slow time scale. All of this is relevant to understand how the system is moving forward in time. Now, I've already been talking about GCF projects and systems. So here we are ultimately interested in the GCF projects, but the project itself, you could argue, is a complex system. The view I've taken is that the system that is being intervened into, without the GCF even being anywhere near, is a complex system already. And you can ask how complex it is. And then the project intervention starts, well then the two together are a complex system, but it will have changed because the intervention does something. So what we do is we do this type of analysis twice. We do it once without anything that the GCF is planning to do, and then again with all the planned intervention. And that gives us certain insights into both the system as well as intervention. I'll show you two brief examples. So we did some case studies and trying out whether this does anything useful. So here is a project that's an intervention in Vanuatu, Climate Information Services, and I'll show you now the seeds. So these are all the variables that were identified by myself and also in the discussion with members of the team. And what we can see is, so we have an environment here, resource system, user system, governance system. And we have before and after. So the project itself introduces two variables only. They only in quotation marks because that doesn't mean that it's easy or simple. And we can already get a sense of that the system itself that's being intervened into is probably quite complex. And then what does that mean for the intervention? So next we look at all the interactions between these variables. So here I show you the interactions just within the systems. So within the environment on the upper left-hand side, we see that global warming will increase, or will affect the sea level, and so on and so forth. Right-hand side, upper right-hand corner is the user system. lower right-hand corner is the governance, and the lower left-hand corner is the resource system. So we can see within the resource system, lots and lots of things are happening. This is just within the core systems. Now I'm showing you everything that happens between the core systems. Right? There's massive interaction. So this picture is totally messy and you can't really see anything apart from that there are lots of interactions. But underneath it is a mathematical object, which is a matrix, an adjacency matrix that has numbers in it, so you can manipulate it and you can analyze it efficiently. You don't have to just stare at this picture to do the analysis. And if you go back to the matrix, you can, for example, identify feedback loops. So here's one feedback loop that's in the system, which is the feedback loop between the health of the land ecosystem services and the income of the tourism enterprises. They are related. And something happens to one, it will affect the other, and that will feed back onto the first one. Okay? These sorts of insights you can get. I'll show you briefly a second project. This is a project in Chile where solar panels are being installed to start a renewable energy market. It's a smaller project in the sense that fewer variables are thought to be relevant. New to the system are solar power energy supply, of course, and then training resources as well, and the related businesses. The interactions here are, because it's fewer variables, they're easier to think about. Again, we have a feedback loop in the lower left-hand corner, and although we have few variables, we have lots and lots of interactions. What can we do with this? First of all, it does give us a sense of interactions are important. So if you are intervening in any one of these single variables, you will have to expect an effect that possibly trickles through the entire. So prediction becomes difficult. And if anything you take away from this, prediction of the consequences of an intervention is difficult. So we thought we'd go a bit deeper and ask, how complex is the sea? Now, I've just told you in the beginning that complexity is a whole range of phenomena, and all of these are parts. So complexity is really just, if you like, an umbrella term for all these underlying phenomena, such as nonlinearity, self-organization, nestedness, and so on. So if we wanted to measure complexity, really what we have to do is to measure the individual. And then we can argue, we add them up somehow. That can be debated, but that is the only way if you really want to get a number for the amount. So here is the suggested way of measuring the complexity of the systems. And again, we will measure them, the system itself, and then again, plus the inheritance. What do? We have on the left-hand side the complexity feature. So for example, number of elements. Okay? We know this is relevant for complexity. In the middle, we have a proxy that we get from the seeds analysis. So the number of elements in the system, well, we take a proxy to be the number of variables in our seeds. It's just a proxy, better than nothing. And on the right-hand side, that will be a translation into the language that is more used to the evaluation field: human stakeholders, resources, ecosystem. So we go through the list of complexity features, number of interactions, or we take the number of links. Diversity is something which adds stability to a system in a complex system. And we take as diversity the number of subsystems. Feedback. I've shown you feedback loops. We just count the feedback loops that we see in the network. And again, we do this with a computational tool, not by hand. Adaptive behavior is difficult to measure, but we take as a proxy simply the links or the interactions in the network that have on one end or the other a human system. So anything that involves human decision making, we count that as potential for adaptive behavior. So these are crude proxies. And you go through this list. Here are the other properties of complexity. Nonlinearity, we take as nonlinearity those nodes in the network that have more than one. Pretty good proxy, I would say. Memory, nestedness. Openness, how open is the system? How exposed is it to things that you can't control? So how many links are coming in from the environment and how many links are within the environment. So we take all these features from complexity, we translate them into our seeds, and then we add them in a weighted form, and out comes a number. Now I'll show you two examples of the same systems that I've already showed you, and show you what the numbers are. So here is the Vanuatu project. On the left, in the left column, you see the properties of complexity, and then the numbers here are what we counted from the seeds, and then we can see here the black crosses and the black numbers are before the intervention, and the orange ones are after the intervention. So, you can look at this for a long time and discuss, but briefly we could say, what can we learn from this? For example, we look at the openness here. We can see that this is scoring very highly on that in that category, and we can at least extract the message that the system is very exposed to the environment. Similarly, for the Chile project, we look at, well, where are the high scores here? For example, adaptive behavior is something that's quite high already, and then the system, the intervention comes in and it becomes even higher. So we can expect there to be, well, the dynamics, the social dynamics will be very relevant, and we know that social dynamics are very difficult to predict. So this adds, if you like, an uncertainty to the project that should be taken into account. And this is, like I say, really a terribly brief tour. I've left out lots and lots of details. But the main things that we can take from this are, first of all, the concepts from complexity science are very relevant, whether you like it or not. So a systematic analysis of what they are and how they play into is certainly worthwhile. Then the seeds analysis itself, there's a lot of subjective subjectivity coming, but expert elicitation and other tools exist to make that relatively objective. Once that's agreed on, the complexity scoring is deterministic. No more subjectivity. And it can do, I've given you two examples of what it can do. It can certainly point you to risk, such as adaptive behaviors that you predict, and uncertainty based on this analysis. So I stop here and I'm happy to take any questions.
Thank you, Karoline, for this excellent presentation. Before I open the floor for questions, I'll invite Joseph to reflect on her presentation, and then we'll collect questions.
Okay, thank you very much, Karoline. I think I have to congratulate you for simplifying a very complex topic in a way that we all understand. So this is a very, very great job. One of the key elements that I got from the presentation is that we need to look at things in terms of integrated and comprehensive manner. First, relationships matter. We need to be able to capture the relationships, integrate them, and then provide a comprehensive way of looking at the problem. And the same also with the solution. And then what I'm also seeing here is that we have to simplify. But the question that I was having while you were talking is, how simple can we go? The more simpler you get, the more you lose information. You lose the robustness of the analysis. So what is the limit? What is the blending height that we need to get to in terms of simplifying those assumptions and then the results that we are getting? And then one of the important elements that came up my mind while I was looking at this is the way we even design projects. If we want to address the investment criteria of the GCM project, how do we do this? Do we need to develop a new framework where we look at things in a more integrated and comprehensive way? Particularly, if you take an example like the sustainable development potential, where you are looking at the social, environmental, and then the economics of the project, the potential of the project. Should we look at them as an integrated and a comprehensive element of the investment criteria. So what I'm seeing from this is that if we are able to think in terms of systems, if we look at project design in terms of systems, then we'll be able to understand the impact of the project, how viable the project will be, and whether they have that paradigm shift that we are looking at. So I think this is a very, very important concept that maybe we will have to think through as a fund. Look at how we inform project design, or we advise accredited entities in terms of how they should design projects, what they need to consider, and then from there we'll look whether the project is transformational or will meet the objectives of the DCA. But I think this is very, very exciting, and I like the example from Vanuatu, which I think will bring a lot of interesting stuff in terms of how we design and implement projects. So thank you very much.
Thank you, Joseph. I know I like the Vanuatu project. Karoline, I suggest you collect the questions and then we will answer together. Any questions?
Thanks very much, Katerina. That's really fantastic and clear talk. You know, I think you've managed to give us some things to hold on to within this very complex subject area. What I've been finding since coming into GCF a few months ago is that financial thinking is often very reductive. Whereas when one starts to look at projects and you're looking at something in all its complexity on the ground, it can be a very different story, and you start to see the diversity in the sense that you are using this term diversity, and I like this very much, the number of subsystems, because this also sort of feeds into this idea of ecosystem, where the ecosystem is really the natural systems plus the social systems, and the way in which the project is interacting with those. So I just have a real concern in terms of how you analyze a project. If we could just go back to the Tarapaka example. I know Joseph really liked the Vanuatu one, and I like the Vanuatu one a lot more. I'm afraid I have a real problem with the one in Chile, Tarapaka. I wonder if you could just please show us that picture.
This picture? No.
Yes.
Oh, sorry. Okay, I see.
Oh, no, I'm not sure.
Not this one, no.
Yeah, okay, sorry, I wasn't able to actually digest that. If you could just show us the one with the diagram, first of all, with all the links and arrows.
Yeah.
That would be really helpful, because that shows that all the different subsystems that you've got for Tarapaka.
This one, yes?
With the arrows.
This is
Yes, that's it. Thank you.
Okay.
So one of the problems with this is that one of the key elements of this project, if it's a project I'm thinking about, is that it was using solar photovoltaics, but that the excess power was linked to building a pump storage scheme, pumping seawater up to the top of the plateau, and at night that seawater would be dropping back down and generating energy. So it's a system of hydro storage, if you like, of the power, of the electric power. I don't see that hydropower dam included anywhere in that. And to me, that's a key thing, because you could potentially be disrupting a lot of ecosystems. It has a big impact on, the kinds of equipment you're going to have to use, because you're using saline water. I mean, basically, this has simplified the project right down, and there are other subsystems which, if you include those subsystems, it actually makes a lot of difference to how you view the project. And just this morning, somebody was saying, oh, we should be replicating this and doing it, in many other places. Well, if you include pumped storage together with both solar photovoltaics everywhere, you're hugely multiplying the number of dams that you're building. And that's not necessarily a desirable thing. So, yeah, just to say how you picture the project and the number of subsystems that you actually include, what is relevant and what is not relevant. I mean, how do you decide that? How do you judge which subsystems you include?
Thank you. Should I?
I'll give you the floor, and maybe Joe, you can comment.
Okay. Yeah.
Take the floor.
Thanks very much for your question. You're pointing at something which is hugely important, which is this diagram, the one before that, which variables go in needs to be decided, together with the people who know the project. Now, I came in, all the information I had was the project proposal, so that's quite old. I can't remember there being a demo, but it could be simply that I missed it. Now, all of this can happen. What I said before was that at this stage, what you need to do is have, I call it expert elicitation. That would be standard procedure. So you have to bring in the people who really know what is being planned here. And they have to say exactly what you just did. Look, you missed out this variable that needs to be in there. And once that variable is in there, I mean, lots of other links are going to be suddenly showing up, right? So it's super important to get that right, where you won't ever get it perfect because there's no perfect answer. But you have to get it as good as possible. So basically what you've just done is you've illustrated how this expert elicitation would work, which is somebody makes a start, and then people like you come in and say, look, you've overlooked this and this. And then once that settles down to something where everybody's pretty much happy with, then you start analyzing.
If I could just come in. So, Anya, this project is different from the one you're referring to. So this is FP17. I think you're talking about FP37. So this one does not have a hydroparadigm. Yeah. So, just go back. I don't know if you were going to refer to Joseph's question. So, by the way, I don't know if Andrea said this. We're really grateful to everyone from the Secretariat who worked with Karoline and with us to understand the project and to think about the linkages. But I have to confess, when we started these discussions, Karoline was very uncomfortable about getting it down to understanding counting categories or dimensions of complexity. But what we realized was that if we just stopped at the attributes of complexity, then it would remain really very much in the complex domain for us and wouldn't translate into something that we could use for evaluation. So in an earlier version, we used exactly what Karoline was referring to, a more reductive version that could be easy for us to essentially count. But of course, anything that's quantifiable is also reductive because you're not attaching a lot of qualitative information to it. But it's the idea is not to abstract so much that you lose out all that richness. That still stays. But to what extent and how can it help us in assessing project design, stability, emergence, as well as transformation ability? These are the questions that we want to try and answer. And there will be another part to this paper that we are looking at the implications for evaluation methodology, whether ex ante or ex post.
Thank you, Joe. I did want to at least echo what Joseph was saying. Several good points. One of them was by how much should we reduce our description? If we do it by too much, then we lose things we might need. If we do it too little, we might not see the forest or the trees anymore. And if you like, reducing it by, for example, leaving out interactions, that would be relevant interactions. That would be a way you reduce it too much and you lose out on dynamics that are possible. But where exactly where is that good zone where you reduce it by enough but not too much? That will be an art. Or by science.
Thank you, Kathleen, and thank you for the IEU actually for organizing this. When coming to this talk, I had a question in mind: what is really complexity? And it was a great motivation really for me to come here. And I think you've broken it down very well. I think I understand. And thank you for that. We are, however, under extreme pressure actually to move towards much more simplicity in the process of assessing funding proposals. And this is basically also probably the way the DCF is constituted, where we only have basically two variables, two impact areas, which are mitigation and adaptation. But only with those two variables, we realize that there is lots of complexity because the variables themselves, they are, as you rightly put it, they are interacting among themselves. They are large scale. There is little evidence actually how they are moving. They are also dynamic. So there is lots of complexity also with only those two variables. However, we have that need to basically come to a much more simplicity. And from your perspective of a complexity scientist, I just want to hear what would be your thinking, how we can basically achieve much more simplicity, because also the climate change issues are very urgent and we need to channel funds much more in a speedy way.
Thank you. Any other questions? This is your chance now. Before I give it back to Joseph.
Yeah, thank you very much. I think I'm very, very excited because this is actually what I'm moving towards in terms of developing a model for assessing DCF projects, using system dynamics as a way of trying to understand the project in terms of looking at the assessment criteria. So I think this is a very, very important topic, in terms of looking at it. But like my colleague just said, simplicity, I think, will not help us to achieve the impact that we want. If we want to do serious mitigation and resilience building, then we really need to look at the evidence of it, evidence-based approach, to make sure that the simplicity doesn't compromise what we really want. Because we don't want to develop a solution that is so simple that it is more adaptation, increases the long-term risk. So I think it is very, very important for us to really look at the end goal, the end game, what we really want to achieve, and then use that as a basis to develop solutions that are more realistic and can help other people. But I'm really, really excited about this topic.
Thank you very much, Joseph. One more question if there is a. Okay, back to you.
Okay, thank you very much for your kind remarks and your question. It's often simplicity is being put as the antithesis of complexity, but that is actually not the case. Simplicity is the goal of complexity scientists. So you're extracting simplicity because that's the only way of, for example, making a mathematical model. You make a mathematical model of an epidemic, you're leaving out loads and loads of things, but what you keep is the probability of a virus hopping from one person to another. You don't care whether it's a man or a woman, whether they are, from Hong Kong, from elsewhere. You're leaving out all sorts of details. So this is what I mean by art. The art aspect in the scientific endeavor is what are the patterns, and that's what makes it suddenly simple. Suddenly, we have just two things: probability of virus hopping, and we have the structure of the airline network, defining more than this, roughly. And suddenly, you already get predictions of how long will it take for this virus to end up in some moment. And that's pretty good. And from what I understand from their work and from what you're saying, writing, it is a reasonable prediction, not just a spherical cow. So simplicity and complexity are related, totally related, because the goal of the complexity scientist is to extract the simplicity of that system. And this brings us back to Joseph's comment, how far down can you simplify it? And it's surprising how far down you can simplify it often. And then the other point you raised, which is the challenge that I see in this, is the time aspect. So if you give this to university, they'll come back with an answer to you in 2 years. Right? So the timescale of university and academic work is much different from what you guys are facing. And there, I think there's lots of scope actually for work to fasten these things, to speed them up and to bring in the right tools at the right time. And you will have to make compromises when you do this. But I think that's a challenge for people.
Just to comment from my side, one thing also Pierre mentioned about we move to simplicity. I think the question is also how could the AEs who are designing the GCF projects use this complexity concept when they are designing the project itself before it comes to the GCF. Going beyond this linear, very simplistic relationship and the theory of change, if they have done their job very well, applying this concept and looking at the different interaction where the bottleneck, the sensitivity, as you indicated, and then translate those by analyzing that interaction, translate that into the kind of activities they want to propose to the GCF, then it will be much more easier for our task managers here to appraise those things. So the implication is that we have to do also some job in terms of building our AE's capacity to understand this concept and apply that in the design of Before I close, if there are any 1-2 questions, we have about 5 minutes. I will give you the floor. And our young colleagues also, don't shy. Pierre is raising. Okay, that will be the last one.
It's just just a quick reaction. That the theory of I agree actually that the challenges on the ground are non-linear. But the theory of change is, at the end of the day, only a theory. And if we are actually using non-linear models today, it's because we have also issues that have a sense of urgency. And I think we pretty much agree that in an idealistic scenario, we should be looking at the whole complexity. But the linear model actually right now, the way the secretary at least is doing it, is a way of just being really practical.
Okay, I'll give you the final word to you. Any final advice, and we'll conclude.
I think my final advice is to not underestimate complexity, but also to not be afraid of it, because it can really be a tool.
Okay, thank you very much, Karoline.